Guys, welcome back to my YouTube channel. We're still under strength of material N5. Today we'll be dealing with shear stress and shear strain. This is activity 1.5. I've captured this picture from your textbook, right? So yeah, I want us to deal with this activity. And if you have not subscribed to my YouTube channel, please subscribe to my YouTube channel and click that notification button so that you'll be notified whenever I post a new video. So activity 1.1, we've given one, says a hole must be punched into a stainless steel plate. When stainless steel plate punched, here what is important, punched. I've discussed about this. If you're watching my video, punched, what is coming in my mind, the area is the one that has a thickness. So okay, you'll see what I'm trying to say. The plate that is 6 millimeter, okay, here is thick, we have a thickness. The ultimate shear stress for the stainless steel is 400 megapascal, which is fine. The punch is made from alloy steel, of which the allowable compressive stress cannot be more than 120 megapascal. Calculate the maximum diameter of the hole that can be punched under these conditions. Conditions, not I did not say under a condition. Conditions, there is S here, and be careful there. So you're supposed to use everything that we have given there. So what is our data? Okay, our data that we are given, I will write this on the next slide, down slide. Let me just grab this data first before I write this solution from the thickness there. Then we've given shear. Remember, shear stress is 400 megapascal, and this is a direct stress, which is compressive. It's 120 megapascal. They want the diameter, so I think I've taken all the necessary information. This is our data. So let me write here on the slide, right? So yeah, it's question 1. They want the data, they want the diameter. This is what we're given. Check, we're given shear stress and the direct stress, which is compressive, and the thickness. They say mental plate is punched. Mental plate, it is punched. Here we'll focus on this area. There will be some space there that will take mental plate there. We'll have the mental plate, whereby the area there. Okay, so as we know that we've given a shear stress is equal to what? What is the shear stress? Actual, according to you, is force over area. However, okay, we want the diameter. The diameter, we know we can get the diameter on the area. So if I make area the subject of the formula, I will multiply there. I will have force over divided by shear stress, right? So I have a shear stress like this. This is what I have. But what about the force? What is force? You're not given, but I know that we've given what the stress here. We know that the stress is equal to force over area. I want to make force subject. If you make the force subject, will be multiplied there. Will or want to make the force the subject of the formula, will be force is equals to diameter. So we'll multiply there the compressive stress multiplied by this area, that stress there multiplied by this area. So this is what we have here. So I will substitute because it's one and the same thing. So I will take this and substitute here. You see most of the maths there that I've taken. So the area here will simply equals to 6 multiplied by area over the shear stress. So be careful. Let me not confuse you before. Be careful. Let me not substitute now first, because you'll be a little bit confused. I will come to that. But what about this? How can we find this area? before I will come there. Let me not confuse you. Remember, this is a wave. It's under shear stress. We know that our area here will focus what is shear. The shed have indicated the shed, the area you must know will be given by pi multiplied by diameter multiplied by thickness. The area here will be pi. Be careful about that. Will simply equals to pi multiplied by diameter multiplied by thickness. Then here we have what? The force over what? Over shear. Okay, but now this is what we have for shear. Is the area for punched. This was the area for punched, guys, for the shear one, for the shear. But however, for direct, we have punched there. The direct one will consider, we know the direct one will consider the area, the cross section. But for the direct, remember this is a direct. This is, we call this direct stress. That is direct. It's a direct stress. However, now the area for direct, the area for this one, you see from that direct, we know that is pi over 4 multiplied by d squared, direct. So yeah, so full understand this. So what I'm trying to say there, we know that, okay, that force will substitute with this. Now I can take this and substitute there, but we must know that it's the direct one. Then we'll have pi multiplied by diameter multiplied by thickness. What is that? Force is stress multiplied by area over shear stress. But remember, this is what is the direct one. Then the area for direct, remember here we still have pi dt, right? It's equal to stress multiply for direct is pi over 4 multiplied by d squared over the shear. Now remember, the aim is to calculate the maximum diameter. You want to make the maximum the subject of the formula. So I'll multiply this side by that, by the shear stress. This will be like this when I multiply, right? Then I will have this direct stress multiplied by pi over 4, then d squared. But we know the laws of maths. If what is common on the, what we have on the left hand side, we must cancel. What you remember, with equal sign, what we have on the left hand side and right hand side, what is the same, we will cancel. So by the way, the diameter, as you can check, this diameter will cancel with the 1 of the diameter. This pi will simply cancel with that pi. So here on the left hand side we'll be left with t thickness multiplied by that. Then here we'll left in the right hand side we're left with 6 multiplied t multiplied by, remember this, there's a division there, t multiplied by diameter over 4. Then if I multiply by that 4 there, you will see what will happen. They will have 4 thickness multiplied by the shear stress. Then I will have that the right hand side will simply equals to shear stress multiplied by diameter, but the aim is to make the diameter the subject. If I make d the subject, I'll divide by this both side. So our diameter here will simply equals to 4t shear over direct stress. So therefore, if I write this, this is simply the same as 4t. So here we can substitute our value. Then is for the thickness, it is, what was the thickness you have given here? The thickness 6, divide that by 1000 will be 0, we divide that by 1000 either way. When we divide will be 0, 0.006. Remember, must be meter multiplied by the shear stress, shear. Here it's a shear 4000 megapascal. Then this is same as times 4000 times 10 to the power of 6. Then we divide this by the direct one, it's 120, as you can see, megapascal. Then we'll have 120 times 10 to the power of 6. Then 10 to the power 6 will cancel, and this will cancel. Simply left with 4 into 0,006 over 120. Then what will you have here, guys? Let me punch to my calculator. 4 into 0,006, right? Divide this by 120. Divide this by, that is 120, or what have I done there? It's 1 megapascal. Let me check that did I manipulate my things? Okay, multiplied here on the top. Fine. Here it is 4 multiplied by 400, obviously. Okay, you see, I've punched this on your calculator. This, remember, not that only. Do not forget that 400. I almost forgot that 400 multiplied by 400. Remember the 10 to the power of 6. This one cancel with that one. So punch this on your calculator. Then I found out D to be equals to 0,08 meter. Let's say now you want it in millimeter. You'll multiply this by 1000. Then this will be simply 80 millimeter. This is what I have exactly. I just punched it there. You can punch. It's 80 millimeter. So that is how the cookie crumbles, guys. Yeah. So you play around with this thing, guys. It's a mess stuff there. Just manipulate your thing and maneuver your way through the answer, right? Then number 2, given 2, then it says the cable shrunk is whatever, shrunk or whatever. In figure 1.32 uses a bolt with a diameter of 10 millimeter. That is a diameter. Link the hook to the load. If the mass has to be lifted is 3 ton, calculate the shear stress brought about in the bolts. Here is this one. You can write it here because you have enough space, the white space here on the side. So this we want this shear. What is shear? I can write it here. What is shear, guys? Actually, shear is force over area. But yes, you check, this is a direct shear. Well, fine, yes, it's a direct shear. But now remember how many plates? Remember here we have, I said when you're given 2 plates, you'll have how many? If you're given 3 plates, I said do not be confused. This thing represent plate. 1 plate, this is the same as plate. 1 plate, 2 plate, and this hook will represent a plate by itself. Remember, there's a hook here. There is a hook that is there. This one. So this will be have what? 1, 2, 3. I said if you have 3 plates, it's equals to 2. We'll have double shear, which 2 shear, which is our area. We'll multiply area by 2. We'll have 2 shear will be equal to 2 shear. So remember that will be shear. That structure will be like this after shear. Will simply will be like this. They will share that side. You will write will be sharing that side, and here we'll have some pieces there. So it's a double share. We'll consider these two areas. So yeah, then shear stress is equal to, what about force? Force is mass multiplied by gravity over area. Area is pi over 4 multiplied by d squared. So there's something difficult here. No, it's just 3 marks. The mass we don't know, but we know that 1 kg, guys, is equal to 1 ton. 1 kg, 1 ton, not 1 kg. 1 ton is equal to 1000 kgs. But we have 3 tons. Then what about kgs? We multiply there, we'll have 3000. This will be simply your mass will be 3 multiplied by 1000, which is same as 10 to the power of what? 3. Then the gravity, do not forget, you must have a gravity 9.81. Remember, they were dealing with the force. We are dealing with the force, then over 4. Your diameter is 10, which will be millimeter, will be like this. Hopefully you can see there. You square these guys, then you can maneuver your way. Punch your calculator. Also let me punch mine. Therefore let what will find this to be. 3 times 10 to the power of what? 3 multiplied by 9.81. Then I say pi over 4. Then because it's double, do not forget to multiply by 2. Our area here, multiply this by what? By 2. Remember, it's a share. Multiply by 2. Do not forget to put that 2. It's simple to forget that 2 actually. One thing I've noticed, it's so simple to forget that 2. You square and okay, then I multiply this by that 2 there. Right, so what seemed like I got, let me check, what did you have there? Let me write this. We have 3 times this times 10 to the, okay, it's fine. Then 10 divided by 1000, obviously there is 0.01. Okay, it's fine. Let me say 2. Make my life 3 times 10 to the power of 3 times 9.81. 2 multiplied into simply pi over 4 0.01 squared there. So I simply got 1187 comma remember here you must, yeah, if you punch that accurately, sorry about that alarm, is what I got 1,8,357, okay, 357 like this, then times 10 to the power of 6, whereby power of 6 is same as megapascal. So yeah, this guy that I found here, how nice is this? So yeah, this is how you go about, guys. Sorry about this one, my calculator made some. So yeah, this is what I found on my calculator. So I've given number 3. Yes, 3 says a shorter concrete, oh this is little, a shorter concrete column is 2 meter long. We have the length, which is 2 there. It's original length actual, but yeah, it's a length there, and has a cross section of that cross section. In other words, that cross section is just an area, right? So that means this, it's a rectangle. You can see why the area is like that. 700 millimeter times 900 millimeter. Okay, no, it's a rectangle. You cannot, you see something like rectangle there. Okay, it's fine. The column support the compressive load of that. Oh, load, we have that force there to be 3 mega newton. Oh, you have to convert this. Mega newton is the same as Remember, same as times 10 to the power of 3 times 10 to the power of 3 is like this, but come. But what do we, okay, what do, okay, is fine. There's nothing times the same, okay. I remember it's not a mass. I thought it was something I want to do, but just leave it like that. We know, okay, no problem. Just leave this. We'll see. The concrete has a density of this. Oh, that is a concrete density. You know, most density is mass over volume. So, guys, plus me, I'm Mr. Fluid Mechanics. I'm killing mechanics, the fluid mechanics. So I think if you don't know this formula, you can check my fluid mechanics N5 and N6. You'll see this formula is often used because I'm also tutoring actually this YouTube channel was designed for fluid, right? But however, I'll be posting all nated most subject and stuff. But yeah. So okay, enough for stories. We won't end. Let us attack our team. We've given that, and then they say and in elastic an elastic modulus of that, which is E12 kilonewton per cubic square. Oh, fine. They try to be fancy, those people there. They say, hey, you buddy, calculate. They say, brother, calculate. We have 3.1, the stress at the base of the Coulomb. Oh, buddy, it's fine. Yes, buddy, it's fine. The amount of 3 kg of the Coulomb. This is what we have there. All right. The density, you can find the mass. Yes, you can find the mass. Yeah. Then the Coulomb will focus, then the amount of the Coulomb, we have that Coulomb as that force, but the concrete is that density. So why we don't the mass? Okay, then that means why do they separate? But should, in other words, they want you to combine. They want you, okay, if that is a load, then the concrete, the mass of this, that complete, it's additive. That's my question. Is the force additive? Short concrete, you see, that means it's additive. It's a force that is applying there will be additive to the one of the, yeah. So because, okay, the stress at the base of the Coulomb, because will be compressed, we know that the stress is equal to force, or is equals to force over air. But here will be additive. We'll have the force of the direct, the one that is applied, and the one of the Coulomb. They must be, because yeah, we'll get that force from this guy there. We can get the mass. But here's my question: if we'll get the mass, where we'll get the mass? Because we don't have the volume after all. But we have the volume, because the volume is equals to area multiplied by the length. So we've given the area, we've given the length. Then we can maneuver our thing. Okay, it's fine, guys. No problem, we'll find the mass. So let us attack this question, guys. Nevertheless, okay, beautiful. Oh, but the 3 marks, all those by they are so stingy for that this type of question, even though they are so scarce. I can remember I will be dealing with answering that there. I can say area we are given there is that can multiply that. The same as 0.7 times 0.9, the same as that. This will simply equals to the same as 0.7 times 0.9. This will give us 0.60. Remember, it will be meter squared. Yeah, meter squared. There-ish. Right, this is our area. We have the area. We know that we've given the density. We know that density is a mass. Why I'm saying it's mass over volume. If I want the mass will be density multiplied by volume. But what will be the volume? The volume will simply equals to area multiplied by the length. We have the area there, which is 0.60 times the length, which is 2. Then remember, this is meter squared, this is meter. Then when you multiply this, will give us meter cubed. All right, this is nice. By the way, but this question I did not thought that they can project such. These people are cruel a little bit. They want you to think, guys. These people, they are cruel. Someone, the person that is setting strength of material is a little bit cruel. Cubic, they don't want you to pass so easy. You see, we have that volume, but we're actually wanting mass. You take this, you substitute it here. So, actual fact, you can erase there. Now our mass, we know the mass will simply equals to density of given there 2200 times now the volume is 1.2. Imagine this is cubic meter. When you multiply this cubic meter and that will cancel, left with kgs. So yeah, so 200 times 1,2, so 200 times 1,2. Okay, this guy has the mass of 264 kg. Then now, how can we find the force now? Then we'll be additive. We want the force now. Okay. Okay, let me erase these guys there. Are we cool about that? But the force, it's mass multiplied by G. Then the mass is that 2640 times 9,81. Then multiply by 9,81. This will be 258 watt again, 898,4. This is Newton. Actually, it's for the coulomb, but it's not the one that is applied. It's the one that is compressive, the supporting, the coulomb support, the supporting load. So we're supposed to add to have the total actual, the force that, remember, we want the one that, imagine we want we have the coulomb there, which is our square coulomb there. Yeah, we want the one in the bottom. Remember, the bottom, as I say, the one in the bottom there, the cross section there in the bottom will experience the one of the compressive plus also the soft. All this force and the mass will act here. You know that if you have a scale here, then here it is you here on the scale. Let's say you've climbed there at the scale there. it is you there. Then you hold the backs or you like that with one hand, both side. It says so. You have that two boxes. This two is 3 kg. This one it says 5 kg. Then your mass, let's say it's 8 kg. So the scale will just sum up all of this, will measure all those kg. The scale does not know, this guy is holding some box, but he will be doing its work there. You see? No. So it's one and the same thing. We can add up that force, the total force Ft, simply 25898,4 plus the one of the compressive, the one that we have given 3. Oh, this will be too much, plus 3 times 10 to the power of 6. So this is how the cookies crumbles. Ft. Ft. What is this? Is double what now here? No, yeah. Yo, this guy. Plus 3 times 10 to the power of 6. Okay, the total one is 3, or you can just put I don't want to round off. Let us put this as it is on the top of the formula once and punch this one time. Remember what do they want? It is the stress at the base. The stress at the base. The stress at the base there will be equal to force over area. Whereby this is 258. Remember, this will be total force 2525898,4 plus 3 times 10 to the power of 6 over the area 0.6. Right, so yeah, let's find this. Let us get this. Well, can 580, okay, 258. Yes. Okay, let me see. This is what we had. 25 by 0.60. Let me just press this 25898,4 plus 3 times 10 to the power of 6, then 0.6. Okay, it's a nice fade to do. At the base. It's a nice fade to do. 500. Oh, what I'm saying, not 500. Come on, Mr. Fluid, what are you doing there? Come on. Okay, it's fine. Measured in Pascal. Let me make this in megapascal. You know your convections. If then you'll divide by 10 to the power of 6. So that you're supposed to know that from N4, guys. It's 5,043 there. Yeah, if you round the content and round it off from there, it will be like this, megapascal. Or you can end it here, then say megapascal, or you can continue. It's up to you. So this is what we have so far. Yeah, now the amount of streakage of the column. Streakage, that means the change in length, how you have changed, you have stringed them, how we have reduced, which is this guy, is force multiplied by original length over area multiplied by E. But do we have this Young modulus of elasticity? Also, do we have this one again? This is interesting, this formula. There is this one. Remember, this is simply equals to strength. You can say, you can write that to be strength multiplied by L over E. So, see, you see the cookie crumbles there. See what is going on there. Up to you. Which one will you apply? It's up to you, by the way. Which one do you want to apply? Stress or what? Okay, they will do them both. We'll compare, but there will be some little slightly difference if I don't know, but we'll check when we put in our values. So far we don't know. Okay, want the X, but here is the problem. Here the E is given in such crazy manner, but not that it's not that crazy, but little, but you get me. Them say crazy is not that is crazy, that you must be good at your conversions here. We've given that 12 kilonewton per millimeter squared. It's not crazy, but might be crazy if you don't know conversions. So this is strain, isn't it? So we have to convert them. Oh, convert. The strain almost is given in what? Gigapascal most of the time. I'm keeping saying strain. Sorry, I'm mad. Even I said it's not a strain. I want to say Young modulus of elasticity. This is not a strain. Oh, sorry about that. I'm keeping saying strain, but I know this is a Young modulus because strain is like this. There's a difference thing between this and that. It's not the same. So yeah, Young modulus of elasticity is measured in gigapascal most of the time, also in megapascal, but often is measured in gigapascal. Okay, let us go. Pascal, what is Pascal? Pascal is simply Newton per meter squared. So we will try to attack this guy. Talking about Pascal, let us try and attack that guy. So I've given here 12 times 10 to the power of what is simply 3. Then we have Newton there. So again here it's a millimeter squared. It's the same as millimeter. Millimeter multiplied by millimeter, but you know that meter is equals to 10 to the negative 3, only one. So right, but this, if you multiply these twos, will be square. Remember, meter times meter is what? Meter squared. So the aim, we said Pascal is given by Newton per meter squared. So let us do this. Let us write that to be squared. So we have the squared and convert this to numerical scientific form. That will be times 10 to the minus 3 times 10 to the minus 3. Then the laws of exponents, the bases are the same. You add the exponents, it becomes 10 to the minus of 6 meters squared. So this is what we have there. times 10 to the minus of 6 meter squared. So now we are good, meter squared, but this is Pascal. As you can see, that is Pascal. No, since that is Pascal, you know, there we have E 1 2 times 10 to the power of 3 10 into times 10 to the minus 6 Pascal. Now we've achieved Pascal. What is left is for us to achieve giga. Remember giga, the giga guy. The giga is times 10 power of 9. If we can find that way, let us apply the maths. 12 times 10 to the power of 3. Apply the laws of exponents. The bases are the same. When you are dividing, I don't know that you know the laws of exponents. Let's say you have a3 there raised to a2. This will be a. You simply a minus the exponents there. You minus. That's the law. So there, as you can see, we'll apply this law there. We have times 10 to the power of 3. This is the same, but minus, but we also have the negative itself. Then we have Pascal like that. To apply that law, then E is 12 times 10 to the power of, distribute that, will be 3 plus 6 Pascal. Then E 12 times 10, this 3 plus 6 is 9 Pascal. But what is that? We say it is giga. So E, ladies and gents, is equal to 12 gigapascal. Simply just 12 gigapascal, that E. So do you get it? If you don't get it, forget it. I'm joking. Forget about it if you don't get it. I'm joking there. Okay, fine. Can I let me use this of the stress? I don't have time for the one of the force. What yeah, it's a lot. Let me see. Can use them as 5,043 32 times 10 to the power of 6 into length, which was 2. There we had, what was that? Here it did 12 gigapascal, which is the same as 12 times 10 to the power of 9. Let me just try this. Okay, we will do also that. Want to check something here. I want to check something. This will be equals to 840,527 times 10 to the minus 6. Change in length, which is in mid. It will depend on your how did you round off, but anyway, there will be some range of answers there. Okay, let us try the second one formula. It was force multiplied by length over area. Okay, now the problem will be what was that total force? It will cause me to have that total force. Here it is. What I'm doing now. Copy that guy. So yeah, the total thing there multiplied by 2 the length. I can say like this divide by area. The area which was 0.60 times 12 times 10 power of 9. Let me check if I'm using this formula, what can we achieve here? 258.98, plus 3 times 10 to the power of 6 times 2, 0.60 times 12 to the power of 9. What can we achieve here? Oh, I got this to be this is 8040,572 times 10 to the minus 6. So nevertheless, this is the one and the same thing, as you can see. So yeah, this is what we have, guys. Sorry about that. So nevertheless, please do not forget to subscribe to my YouTube channel and click that notification button so that you will notify whenever I post a new video. However, if you find my videos helpful, hit that thumbnail there or hit that button. If you find my video helpful, also like and comment showing that we are interested to this type of question, so that I'll project more. Show the thumbs up there, like them, and then you can also comment, you can share, feel free, you can share to any group, to your fellow classmate, no problem, feel free, guys. Thank you for watching. This is what it is.